Hi everybody, this is Dr. Ramey, and I'm going to cover how to use an ocular micrometer to determine the size of a specimen. So when we're using a microscope, if we look in the ocular or eyepiece, we would see an ocular micrometer. So this is this thing here, and each of these spaces, of these tick marks here, like here's one, is called an ocular unit. Right? So this particular ocular micrometer that's in this picture has 10 ocular units if you were to count them. And at different scales we would know, or at different magnifications rather, we would know what the scale of the ocular unit is. For example, I'm just going to make this up, say let's say at 100x magnification, the ocular unit, the distance between each tick mark might be, say, 2 microns per ocular unit. I just write it like this, 2 microns per ocular unit, right? And so if our specimen is 3 ocular units long, so if it looked kind of like this and spanned 3 ocular units, 1, 2, 3, then we would say that it's 3 ocular units long, and at that magnification we know that an ocular unit is, or the scale is 2 microns per ocular unit. So the ocular units would cancel out, and we would say that that specimen is 6 microns or micrometers in length. So if we were to look at a specimen like this, let's say that this is at 100x, and it appears to be 1 ocular unit in length at 100x. If we look at the same specimen at, say, 1000x, the specimen looks much larger because the magnification is 10 times more than at 100x. So if it's 1 ocular unit at 100x, it's 10 ocular units, measures 10 ocular units at 1000x. But the specimen hasn't changed in size, it just appears bigger because of the increase in magnification. So if we know the scale at 100x, then we have to use a different scale at a different magnification to determine the size of the specimen at different magnifications. And that's a fairly easy thing to do as long as we know the accurate scale at any one magnification. And there's ways in the laboratory that we would do this. We would actually use a very small a slide that has a very small ruler essentially on it, a very tiny ruler, and then we could use that to determine the scale, the number of microns per ocular unit at any given magnification of that particular microscope. And we would really only need to do this with one magnification, and then we can use some math to determine the scale at different magnifications, and that's what we're going to take a look at in this example. So, we'll do a couple of examples actually, and this is the first one. If the image shown here was created using the 100x objective, so this is at 1000x, right? That's a total magnification. It says the pink cell. Well, clearly that's wrong. It's the blue cell, right? The blue cell is blank microns across. And note the space between each vertical line, or so that would be each ocular unit, when using the 40x objective is 2.5 microns, right? So at 400x, the scale is 2.5 microns per ocular unit. But this is at 1000x, so we can't use 2.5 microns per ocular unit to determine the size at 1000x. What we need to do is use this scale to determine the proper scale at 1000x. And one easy way to do this is to use a variation of a formula that you're probably familiar with, and that is the C1V1 equals C2V2 formula. Now this is a pretty common formula to determine concentrations at different volumes. Concentration 1 at volume 1 equals concentration 2 at volume 2. Well, we can simply use this formula and just alter the C and V to be, say, mag 1 and scale 1 equals mag 2 and scale 2. And in this case, we can plug in, for mag 1, we can plug in 400x. So I'll just leave the x off, we'll put 400. And the scale, 2.5 microns per ocular unit, to simplify, I'll just put 2.5. And then that's going to equal mag 2. Well, mag 2 is at 1000x, so I'll just write 1000. And then scale 2 is what we're looking for, right? What is the microns per ocular unit measurement at 1000x? That's what our scale 2 is. And when you do this math, I'm actually going to have to do it on the fly here. We would go 400 times 2.5 and then divide that by 1000. And, well, that makes it pretty easy. That equals 1, right? So 1 is scale 2. And that would be, now we need to make sure we plug back in our units right here, right? So 1 micrometer, excuse me. Let me just erase that, go back, and that'd be 1 micrometer per ocular unit, right? So that gives us our scale, and that makes it super easy. It's 1. I didn't intentionally do that, but the specimen here is 1, 2, 3, 1, 2, 3 ocular units, right? So from here to here is 3 ocular units. So then we just need to multiply. So we have the scale being 1 micrometer per ocular unit, and our specimen is 3 ocular units across. Ocular units cancel, and of course that would be 3 microns. So that's the answer. Our specimen, our little blue cell there, is 3 microns on its length there. Let's do one more practice problem, right? It's a similar problem. If the image shown here was created using the 4DX objective, the pink cell is blank microns across. In this case, it is a pink cell, right? So this is the same kind of problem. We're going to use this mag 1 scale 1 equals mag 2 scale 2 formula. We're going to plug in our numbers. Mag 1 is, well, let's see. So this would be at 100x. That's the total magnification. And scale 1 is 4.2, right? So each space, so this would be 4.2 microns per ocular unit. And then mag 2 is 400x. And scale 2 is what we're looking for. So let's see what we get. So we got 100 times 4.2 and then divided by 400 gives us 1.05 microns per ocular unit is our scale at 400x, right? Because this is using the 4DX objective. And this specimen is 2 ocular units. So 2 ocular units is the specimen, and our scale is 1.05 microns per ocular unit. Ocular units cancel, and 2 times 1.05 is 2.1 microns. I hope this video was helpful.